Nowadays, climate change is a hot topic for our society. High amount of CO2 in our atmosphere produce really the increment of strong events. What we want is to reduce this CO2 by the use of green fuels, as for example, the hydrogen. We want to get rid of the petroleum from our life. Fuel cells are electrochemical devices that use this green fuel, hydrogen, in combination with oxygen to produce water and energy. One of the main challenges on this reaction is the component which facilitates the reaction. This component is called catalyst. A lot of investigations use platinum as a catalyst or some other novel metals, but the problem on this material is the high and volatile price that makes them a showstopper for the fuel cells. Our mission, our research is to find new materials, as for example, complex solid solution, or also what we call high entropy alloy materials, in order to completely substitute the platinum or the noble metals for the fuel cells. They have unique properties that make them a really good candidates to be the new generation of catalysts. We are talking about the catalyst. So in order to substitute the platinum from the fuel cells, this new catalyst has to have a certain features. We need to talk then about which size, we need to talk about the arrangement and the composition, and we need to talk about the stability of this new catalyst. In the first point, in the point of the size, this catalyst has to be really small, in the order of few hundred atoms, because the reaction that occurs between the hydrogen and the oxygen occurs only on the surface of this catalyst. So here we can imagine a big block with a certain surface, but if we cut this big block in certain parts, then we'll have more seeds, more grain, more surface available where the reaction can be performed. Then the next question is, okay, if we want this catalyst in the range of few hundred atoms, we need to know how we can synthesize them. For this, we are using what is called sputtering technique. Here we have a big material full of all the elements that we want to use as our new catalyst, and what we can do is to remove these atoms and to grow them again in this size of only few hundred nanometers. Then it's important to see, okay, if these are really small, how we can look at them, how we can really confirm we have the specific arrangement and the specific composition. Here we come at the second point. For this, we need what is called electron microscopy. Electron microscopy is a technique which allows us to achieve this high magnification to visualize atoms. With the optical microscope, we can really see, for example, the thickness of a hair. But if we want to see all the atoms which compose this hair, we need then this electron microscope. That in the sense, they are more or less the same as the optical microscopes, but instead of light, we are using electrons as a source. The last point is about the stability. It's well known that these catalysts, after being operated in the fuel cell, they suffer what the people is called degradation. So this means that they have a short lifetime. For this, what we want is we want to take our material just after the sputtering technique, after the synthesis. We want to simulate the same conditions that we have inside of the fuel cells, and we want to look again, thanks to our electron microscope, to see which are the changes. Do we have a new composition in these new materials? To learn about these degradation mechanisms, to like this, optimize them to increase the efficiency of the fuel cells. Our investigation, as we say, it's about the reaction that occurs with hydrogen and oxygen to produce electricity and water. We find that this reaction needs a certain amount of energy, and our new catalyst materials can start this reaction using less energy than platinum. But for this, we also find that they need a specific composition and arrangement of the atoms. In terms of arrangement, we can have these materials in three forms: face center cubic, body center cubic, or amorphous. If we imagine a cubic box, we can imagine that for the face center cubic, we have one atom in each corner, and then we'll have one extra atom on the face of each cube. For body center cubic, we'll have the same atoms on the corners, but we will have an extra atom on the middle of the cube. And for the amorphous structure, here we don't have any kind of cube. We will have a randomly distribution of the atoms without any order. And also we find that in our case, the best arrangement, it was body center cubic with a certain composition. So what we need in order to completely substitute the platinum from our daily lives, we need a body center cubic structure with high quantity of chromium and cobalt and with low quantity of manganese. Like this, we will have the perfect candidate for our new fuel cells. If you want to stop the CO2 emissions, if you really want to get rid from the petroleum from our life, we need hydrogen. To make hydrogen more competitive, our research show that we can really decrease the price of the fuel cells, removing the platinum from them. Adding our new materials will have the same and even better efficiency with a lower cost. So far, our investigation was made in a lab scale. So for the future, what we want is to scale up our methodology and to arrive to several industries. Another strong point is that we can really design the material as we want. We can choose the composition, we can choose the arrangement of the atoms, we can choose the size of this. And this is a really good opportunity to apply these materials in a different field.